Good morning and thanks for attending this presentation. This work is entitled SPARTAN, Rapid Trajectory Analysis via Pseudospectral Methods. For what regards the contents of this presentation, first I would like to say something about the research motivation and the roadmap that we envision for SPARTAN. Then I will introduce the mathematical background behind the tool. I will present three different numerical examples of growing complexity, and finally there will be some conclusions and some words about the outlook for the future of the tool. So let's say something about the research motivation and the roadmap. Optimal control has a strong mathematical background. It is a very powerful theory which allows to deal with a huge amount of different problems. A typical example is represented by the classical brachistochrone problem, where we are essentially interested to find the solution that minimizes the traveling time of a sphere subject to gravity, which has to go from point A to point B. Historically, the first methods that were developed to deal with this kind of problem are called indirect methods. The idea is that they are used to develop the necessary conditions to transform the original problem into a set of coupled differential equations, and the solution to these equations is a candidate solution to the optimal control problem. These methods historically exhibit a high accuracy but also have some drawbacks. First of all, they require a very good initial guess in many cases. In case we have inequality constraints, they might be not so easy to treat, and minor changes to the problem might impose a derivation, more or less a derivation from scratch of the necessary conditions underlying the optimality of the problem. These drawbacks, together with the development of modern CPUs and nonlinear programming solvers and even more more advanced transcription methods, boost the development of the so-called direct methods. In the direct methods, the problem is attacked numerically, where we do a transformation of the original continuous problem into a discrete version of the same problem, and then we solve it with the nonlinear programming solvers which are available. Among the most famous and most successful software to deal with to implement the direct methods, there are the US-based packages Dido from Elisar Global and the GPOPs developed by University of Florida. The idea behind Spartan is to basically provide a EU-based open source alternative which is able to solve, by using direct methods, a huge amount of different scenarios, and to be able to support rapid prototyping of optimal solutions. So I would like to say something about the roadmap and the historical development of Spartan. This tool started to be developed in 2012-2013 as a supporting tool for a specific project developed by DLR, ChefX3. You here on the right side you can see the ChefX3 original hypersonic vehicle. At the same time, we started to generalize its interface in order to be able to deal with different problems, and we started to use it in internal DLR projects, including a lunar landing reachability analysis and a joint DLR-JAXA asteroid descent study to land on a Trojan asteroid. From 2015 to 2018, we continued to improve the software and validate it with different examples taken from literature. For example, on the right side here you can see the optimal trajectory corresponding to the entry guidance of the space shuttle, as well as the optimal descent and landing sequence for the Mars Science Laboratory experiment. Moreover, at the same time, until 2018 we could not implement multi-phase problems, so in the last couple of years, with the help of my students, we extended the functionalities of Spartan to deal with the multi-phase problems, and this new feature gave us the chance to implement multi-stage rocket ascent scenarios. For example, in the two top figures here you can see the optimal ascent sequences corresponding to the Saturn V rocket and the Delta III rocket. At the same time, the development of landing technologies for rockets gave us the chance to implement also more complex sequences for descent scenarios. In this case, for instance, you can see the Falcon 9 boost back and descent sequence depicted in the bottom figure. At the same time, we started several cooperations to compute optimal solutions for institutions like TU Delft, the University of Madrid Carlos III, the Korean Aerospace Research Institute, and the University of Udine. And this gave us the chance to test the tool on even a more diverse series of optimal control problems to be solved. So what is the mathematical background behind the Spartan? The core is essentially that we deal with a multi-phase optimal control problem. In the most general Boltzmann form, we have a cost function which has two contributions, a Mayer term and a Lagrange term, which in this case is split into several contributions associated with the different phases that we might have in our problem. At the same time, our problem consists of a set of differential equations describing the dynamics of our system. We might have some path constraints, which might be linear or non-linear. We have some boundary conditions acting on the different phases of our problem, and finally, in case we have some discontinuities, we might also have some linkage conditions, which a typical example is, for instance, the mass discontinuity associated with the stage separation event. This continuous problem is transcribed by using a flipped Dirac pseudospectral methods, and therefore the transcription process consists of transforming each part of our infinite dimensional optimal control problem into a discretized finite dimensional nonlinear programming problem that we can solve with one of the off-the-shelf software available like SNOpt or IPOpt. So we said that in the transcription we will transform each of the continuous pieces of our optimal control problem. For what regards the integrals appearing in the Lagrange term of the cost function, we will apply Gauss quadrature rule. So our integral will become essentially the product of the integrand function evaluated in our discrete points multiplied by some weights. And these weights have a very simple rule. They can be computed in a straightforward manner by using this formula, and this kind of approximation exhibits a high degree of accuracy due to the rules of the Gauss quadrature rule. At the same time, we have some differential equations that need to be transformed, but we do that by using the so-called differentiation matrix, which essentially allows us to transform the left-hand side of our differential equations into a linear combination of our states by combining them by using the elements of our differentiation matrix. And by using this transformation, we need to select some discrete points xi where to discretize and evaluate our solution, essentially our states. These points are selected as the roots of our flipped Radau polynomials, and we refer to these points as collocation nodes. So we have now a resulting nonlinear programming problem to be solved. In this case, the cost now is completely discrete since we applied the Gauss quadrature rule to the Lagrange term of our cost function. At the same time, our differential equations are now a set of nonlinear algebraic constraints thanks to the use of the differentiation matrix. We might still have the path constraints, which will simply be evaluated at the collocation nodes that we are using, and same holds for the boundary constraints that will be evaluated at the extreme nodes of our domain, and at the same time we will have the linkage conditions, which will be simply transformed into the corresponding discrete counterpart. Since we have transformed the problem into a discrete nonlinear programming problem, we have now a set of a vector of constraints embedding all the conditions that we are imposing into our nonlinear programming problem. And of course, there will be a discrete vector of variables which include all the states and controls that we want to obtain. And at the same time, this vector of variables will also contain some times, which basically are the time associated with each phase that we are implementing in our problem that might be fixed or might be required to be determined by SPARTAN itself. With the vector of constraints and the vector of variables comes a Jacobian matrix, which essentially relates these constraints to the variables, and this Jacobian matrix has a structure that can be exploited to speed up the computation and also to improve the accuracy of our computation. As I said, the Jacobian matrix has a structure to be exploited, and we can improve the accuracy of this computation by also using a complex step or dual step for the numerical differentiation of the nonlinear terms that we have. So let's have a look at three different numerical examples that we are showing to emphasize different features of Spartan. The first example is a double integrator. We have a system subject to a double integrator dynamics where we are essentially interested to minimize the time to bring the system from a given set of initial conditions to rest. Typically, in these formulations, we have a bounding control, for instance, between -1 and 1, but in this case, I modeled it in a different way. Since we know that the optimal solution will switch from -1 to 1, I was imposing the values of the controls in the two phases while having the time between the between phase 1 and phase 2 to be determined by the by Spartan itself. The solution here depicted in the state space representation essentially confirms that the tool is able to accurately obtain the switching time, and this is even more visible when we look at the states and the controls over time. So you can see that the phase 1 is in blue, the phase 2 is in orange, and the switch occurs precisely at the time which is also corresponding to the analytical time that we can compute for this simple problem. And this type of feature shows that if we know some information about the optimal control structure, this type of information can be embedded in the description of our optimal control problem to be solved with the direct methods, and the outcome is a more accurate solution because of the discontinuity will be accurately captured by our transcription. The second example that we want to analyze is a low thrust orbit raising problem. In this case, we are also interested to minimize the total time required to raise the orbit of a low thrust spacecraft, where the dynamics is essentially the classical set of in-plane nonlinear differential equations depicted here on the left side. For what regards to the boundary conditions, as I said, we are interested to raise the orbit from 1 canonical unit to 4 canonical units, and for what regards the controls, they are essentially box constrained. When we look at the solution that is depicted here on the right side, we can see that first of all, the solution is immediately found, even though no meaningful initial guess was provided to the software. We verified automatically and numerically the solution by propagating the original continuous nonlinear equations of motion by using the optimized controls, and then we compared the states that we obtained by using the ODE45 propagation with the optimized states computed by Spartan. So on the right side, you can see that all the 4 states match quite well, and that the difference between them is visible here in this plot. So we have for all of them very small differences, with the largest error in the order of 0.2 degrees for what regards the true anomaly of our system. that was from the numerical perspective, but as I said, we also want to use some information and some tools coming from indirect methods. So we apply the covector mapping theorem, and if we analyze the problem by using the Pontryagin minimum principle, we know that the switching function that dictates the switching in the controls are the costates on the radial velocity for the first control and the costates on the tangential velocity for the second control. So for the first control, we can see that the switching in the control signals perfectly matches the changes of sign of our switching function represented by the costates that we obtain by applying the covector mapping theorem. For what regards the second control, the tangential acceleration, since the corresponding switching function never changes its sign, indeed it is always negative. Consistently, the corresponding control never changes its sign, and indeed it is not easy to see here, but it constantly keeps its value equal to 0.01. This type of analysis also can help the user and to analyze effectively if the solution that has been computed numerically is indeed a true optimal solution to our original continuous optimal control problem. The third example that I would like to present today is the computation of the optimal belly flop maneuver for the SpaceX Starship test flight. In this case, we are interested to maximize the final mass, which in the end means minimizing the fuel consumption during the flight of a system subject to a in-plane dynamics where we have three different degrees of freedom, two translational degrees of freedom and one in-plane rotation of the system. In this case, we have a set of boundary conditions associated with the initial horizontal attitude of the Starship spacecraft and the final conditions associated with the pinpoint landing maneuver that we want to achieve. For what regards to the controls, that in this case are the throttle of the Raptor engine, this is between 40% and 100%, while the deflection of the Raptor engine is assumed to be within 20 degrees. So the solution that we obtained with Spartan is depicted here in these two plots. We can see that all the constraints, for instance, associated with the controls are satisfied. We perform the flight maneuver by using about 8 tons of fuel, and on the right side you can see the numerical analysis of the solution that is compared with the propagation of the full nonlinear equations of motion, and you can see that the states agree quite well. This is confirmed by the difference between optimized and propagate solution, which where we can see that in open loop the maximum error is in the order of 5 meters for what regards the position, and in the order of 0.6 meter per second for what regards the velocity. A visual comparison of the solutions will also confirm that indeed the computed solution resembles quite well the original flight of the Starship. In this case, I'm showing the SN10 test flight that is visible on the right side, while on the left we have the optimal trajectory of Spartan. Indeed, the two solutions agree quite well. So, to conclude this presentation, we presented the Spartan, that is meant to be a valid EU-developed alternative to US software like Dido and GPOPs to quickly analyze optimal solutions for different scenarios. The tool supports rapid prototyping of multi-phase optimal control problems and is equipped with subtools to analyze the optimality of the computed solution. We showed the 3 different examples of growing complexity, which emphasize these different features, like the automatic validation of the solution through Runge-Kutta propagators for numerical check, as well as the use of costates for the theoretical analysis of the solution. The use of the indirect methods features in a direct method infrastructure leads to a promising merged approach where we use direct methods for the synthesis of a solution and indirect methods for its analysis. For what regards the outlook, Spartan will be released as a free open source tool under GPL v3 license, and the target is the end of this year. The hope is that we will provide a valuable tool to the European community of researchers, students and companies, and at the same time we want to collect valuable feedback coming from a wider plethora of users. At the same time, we are planning the work for Spartan 2.0 to be started within this year with new features and a more object-oriented design that will make the implementation of these features easier. This concludes my presentation, and I would like to thank you for your attention, and if there are any questions I would be glad to answer. Thank you.